All right, so this is section 7.4, and in this section, one of the main objectives of this section is to study some properties of Euler's phi function. So start with, recall in chapter 6, we considered this. Considered the function f n is d divides n f of d, where f is an arithmetic function. Look at f is a number theoretic function. And we studied some properties of this. For example, we said that if little f is multiplicative, then actually big F is multiplicative, and conversely, we use the Mobius inversely formula. So in this section, we're going to consider the case. Consider this function, capital F, when f of n is Euler's phi function. All right? So in other words, we're going to be looking at this function, f of n is equal d divides n phi of. So we need to determine what kind of a function is this. So let's just start with an example. Let's take n equal 12. Then f of 12, it's going to be the divisors of 12 is 1, so it's going to be phi of 1 plus phi of 2 plus phi of 3, phi of 4, phi of 6, and phi of 12. And phi of 1 is equal to 1. Phi of 2 are the number relatively prime to 2, and less than or equal to 2 is only 1. Phi of 3 is 2 is a prime. Phi of 4 is 2. Phi of 6 is 2. And phi of 12 is also, actually, the phi of 6 is 4. Okay, I'm going to double check these numbers. And this is 4. So let me see it here. We have 1, 2, 1, 2, 2, 2, all twos, and 2 fours. 1, 1, 2, 2, 2. Well, so phi of 1 is 2, phi of 3, and there's something wrong in here. Let me repeat this. So phi of 1 is 1, phi of 2 is 1, phi of 3 is 2, phi of 4, the divisors of 4 is 1 and 2. Okay, that's 2. Phi of 6, the divisors of 6 is 1, and relatively prime to actually 6. So it's only 1 and 5. So this is 2 in here. And in this one, it was actually correct. All right, so when we add these up, so this is 2, 4, 6, and 6 is equal to 12. All right, so the same as actually the number itself. Well, let's look at another example just to see if this is true. So let's take 15. So for n equals 15, f of 15 is equal to 1, phi of 3, phi E of 3, 4, 5, and 50. All right, field 1 is 1, 3 is 2, 5 is 4, and numbers that are relatively prime to 15, and that's going to be 8. So I'm going to really add, this is 12, and the 3 is 15. So it looks like we might guess, take an educated guess that f of n, d divides n, p of d, is in fact equal to n. All right? And in fact, this is the case. And we're going to prove this. And before we present actually a proof of this fact, I want to look at an example to illustrate the idea of the proof. Okay? Means the example, we're going to go through a procedure or steps that will be also for the proof itself, the general proof. We're going to do the same thing, all right? And here's the example I want to look at. Let's look at actually 12, okay? So we're going to take n equal. So we're going to start with considering all the integers from 1 to 12. And we're going to put this in a set, we're going to name it S. Then for each divisor, d of the 12, we define a set. We're going to call this is S sub d as follows. So this one consists of the integers m in S such that the greatest common divisor of m and n, which is 12, is equal to d. All right, so for each divisor, we're going to define a subset associated with this divisor to be those integers from 1 to 12 that are relatively prime, with the greatest common divisor of those integers m, with the 12 to be equal to d. All right? We're going to see that these sets, they're going to actually partition, okay? S means an element in S is going to belong to only one of these, okay? One and only one of them. And when I consider all of them, means consider all the divisors and look at the different S sub d's for these different divisors, the union of these is going to be all of the S. All right, such subsets of S is called a partition of S. All right, so for in our case in here, the divisors we have S1. Okay, so this consists of the integers m in S, such that the greatest common divisor of 1 and the 12 is equal to, m and the 12 is equal to 1. So we need to look at integers that are relatively prime, basically, to 12 from 1. And these are 1 and 5, basically 7 and 11. All right? Let's look at S2. So this is consists of m in S such that m and the 12 is equal to 2. Also, we can write this as m in S such that I could divide this by actually to 2, so this means m over 2 and 6 is equal to 1. So those integers which are actually relatively prime to 6m over 2. And these numbers are 2 and 10. All right? Let's go back and actually figure out how many elements each one of this has. This has 4 elements, all right? And it happens that the 4 is actually equal phi of 12, or actually 12 over 1, so this has 4 elements. And this one, which is very clear from here, it means that the integers, that is what this looks like, okay, it's going to be divided by 2, so this integer relatively prime to 6, and it means that this is, the number in here is going to be phi of 12 over 2. And this is equal to 2, which is phi of 6, which is equal to 2. Okay, so we're going to observe this as we look at the other ones, because this is true in general, that's what it is. So let's look at SC3. So SC3 again consists of the integers m in S such that m and 12 equal to 3. Or also we can say this is the same as such that m over 3 and 4 is equal to 1. And the integers that belong, which are relatively prime to 4, and it's going to be 3 and 9. And again, this has phi of 12 over 3, which is phi of 4 elements, and that's equal to 2. S4, this consists of, again, such that m to 12 equals 4. And same thing here, such that m over 4, and this is a 3 equal 1. And the integer that belong to this is 4 and 8. And again, this has phi over 3, which is a 12 over 4 elements. Then we have other divisors of 12 is 6. And this, again, is such that m to 12 equals 6. Or this set is the same as this one, m over 6 and 2 is equal 1. And this has only one element, which is 6. And this is the same as phi over 12 over 6, which is 2, and phi of 2, and this is equal 1. And last one is S12. And this consists of m to 12 equal to 12. And again, this consists of one element. We could repeat the same thing. And this is the same as phi of 12 over 12, which is phi of 1 is equal. And the union of all of these is equal to the to S, and they are disjoint. Okay, so let me write this down. That S itself is equal to the union so S is equal to S1 union S2, S3, S4, 4 is 6 is 12. And this union is disjoint, so that we put a dot in the union side means each one of these sets are disjoint. So when we take the number of here, this is going to be the sum of the numbers in each one of these subsets. Okay, so this is going to be S sub I equal 1. Well, the sum we cannot write it I equals, so let me just write it like this. Okay, SI, where the sum runs from for the divisors actually, or SD, maybe this is the better way. D divides 12. All right, and we know that each one of these, all right, it turns out to be phi of the 12 over D, and where D is a divisor of 12, and then of course when we added these up, we came up with actually is equal to 12, which is what the order is. So this is the idea of the proof. So we're going to go ahead and actually do the proof in general. All right. This theorem is actually due to Gauss, if you write the theorem. This is theorem 7.6. And it's a theorem of Gauss. For each positive integer, and we have the sum D divides N of phi of D is equal to. And the proof, gonna follow the same steps as we did with in the example. Okay, so we're gonna let S consist of the integer from 1 to N. Then we get a partition. S into this joint subsets for each divisor D of N as follows. We're going to define S sub D, be the integers M and S, such that M and N is equal to. All right. Now, remember that the sets are disjoints, okay, and if D does not equal D prime are two divisors of N, then S D does not equal to or actually intersection S D prime, this one is going to be actually empty. And the reason for this, in general, because this is the reason. If M belongs to SD, this implies the greatest common divisor of M n is equal to D. And we are assuming, if, of course, here's that D prime does not equal to D. And since D prime is not equal to D, then the greatest common divisor of M n cannot equal to D prime. All right? So this means that M is not in S sub D prime. So if an element in S sub D, then it cannot be in the other one. All right? And we know SD, at least it contains, of course, one element, which is actually D itself, the divisor. All right? Because the D with N is going to equal to D. All right. One other thing, that also the set S is the same as, so this set is also equal to M and S such that M over D, N over D is equal to 1. Now, by definition, this, the number of elements in from 1 to N, basically, that are relatively prime, all right, to N over D. So this has D of N over D element. All right. Now, so we have again this S is the union of all of these. So we have S is equal the union of D divides N of S sub D, and this is a disjoint union. Okay, so this is disjoint union. And this implies that the number of elements in S is the number of elements in this disjoint union. And this one is equal to the sum S sub D, D divides N. But we have each one of these is equal that. And one other thing, remember that we've shown this is true for any arithmetic function. N over D, as D, ranges over all the divisors of N. The same thing, N over D is going to be ranges over the divisors in a reverse order. So this one is the same as D of D. All right, and this proves this theorem. Now, this proof that we presented in here, as you see, did not use any properties of the phi function. It basically used a counting argument. All right, this is what we call is we are partitioning a set, and then we are counting it from the set itself, how many elements in the parts of the partition. All right, there's another proof we're going to present that uses the idea or the fact that phi is multiplicative. Okay, so here's another proof for the same theorem, but it's not as self-contained. We call this is kind of proof self-contained. Means we don't need any extra. Think about the phi function. It's just the basic definition of it. All right. So here's another proof. of n equal d divides n d of d. Okay. This one. All right, so let's just start with the case when n equal 1, for n equal 1. Of course, 1 is, I want to check if this is true. DOT. All right, well, the right-hand side in here, the left-hand side is 1, because the right-hand side is equal to, we only have one divisor of d, which is d equal 1, so means we're going to do trivial sum of 1, phi of 1, and this is d equal 1, and so yes, the statement is. So I'm going to assume that n bigger than 1. And we're going to take the prime factorization, all right? One other thing in here, so we're going to let f of n equal to this. Since phi is multiplicative, f of n, because I don't know what this sum is, so I'm just going to put it to fun and show that f of n is equal to n. All right? F of n is also multiplicative. So we have shown this back in chapter 6. So what I'm going to do, I want to look at, I'm going to let n equal I equal 1 to r, p sub I, k sub I be the prime factorization of n. Now, since f is multiplicative, then f of n is going to be f of all of this, I equal 1 to rb ik sub I, and these are, all the primes are distinct, so I can take f of each one of them, and then multiply them up. So in other words, I can switch the product in here, 1 to r f of pi k sub I. So in other words, we need to concentrate now on just evaluating f at powers over primes. Okay, so let's do that. And then we bring this back in the multiplication, and then we get f of n. All right, so let's consider this. Consider f of p sub I k sub I. Again, by our definition of f, this is equal to summation d divides pi ki phi of d. All right. Now I know what are the divisors of our prime is. So this is equal to the summation of phi of 1 plus phi of pi plus phi of pi squared, and so on. All the different powers up to k. And also we know that if this is 1, this is pi minus 1, this one is pi squared minus pi, and so on. pi, let me put one more, to the third minus pi squared, and to the last one, pi ki minus 1. I ki minus. Now you notice that in here the 1 and negative 1 is going to cancel out. The pi and minus pi cancel out. So this kind of sum is called telescoping sum. Like a telescope, you put it, back in, kind of you collapse it, and it does collapse. This one, it's going to give me one term left in this sum, and that is pi to the ki. To convince you this is what it is. So the first one goes with the second one. The pi minus pi, this one goes with this one. This one is going to go to the next one, so the one, and this one is going to go to the one before that. So we only end up with this. So this is pi ki. All right, so we have f of pi to the ki is equal to itself. Now, f of n is equal to the product I equal 1 to r of f of pi k sub I. But now we have the f of pi to the k sub I. This one is equal to pi to the k sub I. And this is equal to that. And which means that an f of n, remember that this one was equal to the sum of phi of n and d divides. So we have this is equal to n. All right? All right. Now, this suggests to bring in Mobius inversion formula because we have a sum, sort of. And we're going to apply the Mobius inversion formula to this sum. But actually, before we do that, there is another theorem on the way, kind of in the middle here. And this is theorem 7.7. One other thing, by the way, you can actually use this, but this is kind of cheating, that since n is equal to this, so you can use, this, corollary to it, that phi is multiplicative. The reason is because n in here is multiplicative. It is actually completely multiplicative. Then we have a theorem which says that the sum, the phi in the sum is also multiplicative. I'm saying this is cheating because we already used this fact that phi is actually multiplicative. Actually, we did not use this. Actually, it is a legitimate one. I used the capital F. Well, yeah, we did. We did indirectly because we said that capital F of n is multiplicative because phi is multiplicative. So, but, here it is kind of another way to see this. All right, here is another theorem, 7.7. And read this for n bigger than 1, the sum of the positive integers less than n and relatively prime to n is equal to 1/2 n phi of n. All right? We state this is in a slightly different way. That is, now the positive integers that are less than n and relatively prime to n, all right, this is actually the least positive reduced residue system mod n. That is the sum of the elements or integers in the least positive residue system mod n is 1/2 n phi of n. All right. Before again we prove this, I'm gonna look at an example to illustrate the technique that is going to be used in the proof. And once you understand the example, you will be able to follow the general idea. All right? Here it is. The example, let me take actually n equal 9. We know that phi of 9 is equal 6. And now I'm going to take the integers that are positive, less than 9, and relatively prime to 9, which means the reduced residue. System mod 9. This is the least positive. Okay, reduced residue system is 1, 2, 4, 5, 7, and 8. Right? Then we can consider these numbers. 9 minus 1, 9 minus 2, 9 minus 4, 9 minus 5, 9 minus 7, and 9 minus 8. Now, when we calculate these, as you guess, we're going to get the same numbers in a reverse order. So we're going to get 8 here, 7, 5, 4, 2, and 1. All right? Now, if I add the original numbers in the reduced residue system, 1 plus 2 plus 4 plus 5 plus 7 plus 8, we get the same thing as adding them with 9 minus. I want to write it this way: 9 minus 1 plus 9 minus 2 plus 9 minus 4 plus 9 minus 5, 9 minus 7, and 9 minus 8. Because they are the same number, just to have it written in this one order. Now, in here, I want to pull out the 9s, and there are phi of 6 of them. Sorry, phi of 9 of them. There are 6 of them, there are phi of 9. So we have 9 phi of 9 because this is equal to 6 of them. And then the other ones, it has a minus sign, and then we have 1 plus 2 plus 4 plus 5 plus 7 plus 8. Now we have this equation which says that so I want to have this one, 1 plus 2 plus 4, 5, 7, 8 is the same as 9 phi of 9, because this is 6, okay, minus those numbers. Well, I'm going to take this to the other side of the equation. So I'm going to take this to the other side. So what I get it twice this sum. And this is 9 phi of 9. And then I divide by 2. And I get the formula that is the sum of these is equal 1/2 n times phi of n. All right? So very simple argument. And actually this is the general argument. It follows this way. So one little thing we need to make sure of. To show that this n minus each of those numbers is in fact a reduced residue system. All right? So here is the proof in general. Let A1, A2 up to A sub phi of n be the positive integers less than n and relatively prime to n. I have a claim here that the greatest common divisor of A, any A, n is 1 if and only if greatest common divisor of n minus A and n is equal to. Now we'll apply this, of course, to these A sub i's. Okay? Now I do it in, for a fixed integer A, and then we're going to apply it to all of these. All right. But let's assume that the greatest common divisor of A n equal to 1. All right? Then this implies, actually this is if and only if. Let me say this is if and only if. There exists x, y in Z such that the linear combination of ax plus ny is equal to 1. And I'm going to play with this, and this is if and only if, minus a times minus x plus ny is equal to 1. I'm going to be actually adding or subtracting an nx from here, and then adding an nx to the same side, okay? So altogether, we could write this one as n minus a minus x and plus n x plus 1 is equal 1. Now I would name this as x prime, And I could name the nx plus y as y prime. So then by the Zoot lemma or identity, this means that the n minus a, and this implies if I only have n minus a, n is equal to 1. All the argument I have is actually if I hold the f. So in other words, this is just a forward one direction. So all of this is an f and all the f. All right, now we have if the original ones, remember the elements of the reduced residue system here on n, they're going to be relatively prime to n. Then when I take n minus each one of them, this also becomes a reduced residue system. All right? If they are relatively prime and they are not congruent to each other, and which I'm going to show in a minute. So therefore, for every I between 1 and t of n from the claim, we have n minus a sub I n is equal to 1. Moreover, we have n minus a sub I is not congruent to n minus a sub j mod n for every I does not equal j. Of course, because if it is, if n minus a sub I is congruent to n minus a sub j mod n, then we can cancel the ends, and we can multiply by a negative, and then we come up with ai is congruent to a sub j mod n. And this is a contradiction because the a sub I, sub j belongs to the same reduced residue system. All right? So the net result in here, so therefore, the n minus a1, n minus a2, up to n minus a sub t of n is a reduced residue system mod n. Now we're going to add these. What I'm doing this is extra, we don't need it because when we add, we basically get, well, it tells us that they are distinct, at least that's what it is. All right, because they are not going to be any of them are equal. So, and it follows then it's a reduced residue system. Now, so each one of them, it's going to be congruent. So this, we also have to have that the n minus a1, n minus a2 up to n minus a sub t of n are equal to A1, because these A, maybe they are not, ordered in the same way I did the example. A, T of N, in some order. So these are equal to each other in some order. Then we can, from here, add the A1 plus A2 up to AN is going to be the same as adding the reordering of those. minus A sub field. All right, this is field N. All right, the same idea in here. We have, we're going to collect all the n's in here, and there is phi of n of them. So we have n, phi of n. And then we have A1 up to A phi of n. Then we're going to take this to the other side. So we're going to take it twice. A1, A2, up to A phi of n is equal n phi of n. And then by dividing by 2, we get the formula for the sum. All right, next we want to consider the apply the Mobius invariant formula to the previous theorem, previous identity that relates n to the sum, says that n is equal to the sum of the values of the t function. Our next objective is apply Mobius invariant formula to this. Remember, this Mobius invariant formula allows us to solve this identity for phi of b. Okay, what is phi in terms of n? And this is actually the next theorem, all right? Theorem 7.8 says this for any positive integer n, we have this. Phi of n is equal to n d divides n u of d over d. All right? This is very simple proof. So we have a equal f of n, okay, is equal to n, and this is equal to p of d, d divides. Now remember by the Mobius invariant formula, this implies that the phi of n, it says it is the sum d divides n of the f of mu. And we would have two different variables. One of them is mu d f of n over d, and the other one is f of d n over d f of d. So let's use this one in here. But the f is the identity function. So the f n over d, so this is equal n over d. And now since n is independent of d, okay, in other words, independent of the index of the summation, because the summation is over d divides n, all right? Then we can take that one out and we get exactly what we're looking for. So this means we have phi of n is equal, we can take the n out, and then we get what the theorem states we should get. 1 over d, or we could write it over d. All right, so what's nice about this theorem, it allows us to prove that give us another way to derive the formula for the value of Euler's phi function. Remember, we derived the formula using phi is multiplicative and basically its definition. In here, we want to use this to prove that formula. Right? If n is equal I1 to r, d sub I is sub I is the prime factorization of n, then as we know, phi of n is equal to n, then multiplied by I equal 1 to r, 1 minus 1 over d sub. Right, so this is nothing new, it is just a different one. So earlier, so it follows from the previous theorem. And the proof again, we're going to use the fact that phi is multiplicative. So I want to do two proofs. One of them use the fact that phi is multiplicative, then the other one we're going to use that the fact that mu, the Mobius function, is multiplicative, not phi. Okay, so here's the first proof. So since phi is multiplicative, then we have phi of n, which is going to be phi of this product. And then we can take the product out and look at, we need the case of I here. All right, so we need to look at the I case of I. All right, so in other words, we're going to apply theorem 7.8 to P sub I, K sub I, okay, instead of that. In other words, we're going to look at phi of Pi K sub I. This is equal to, remember the formula says n, so n in here, Pi K sub I, then summation, T divides Pi K sub I of mu of D over D. All right? Well, let's look at this summation. Let's look at what's inside the summation. Yeah, once we have that, then we're all done. All right, now let's look at this sum. D divides Pi K sub I mu of D over D. Well, the divisors are 1, first of all, mu of 1 over 1, plus mu of P sub I over P sub I, then mu P sub I squared, P sub I squared, and so on. The last term is going to be mu Pi K sub I over P K sub I. Pi K sub I. Now we know that the mu of any square, if it has a square, then it's going to be equal to 0. So all this one is equal to 0, the next one is equal to 0, all this equal to 0. So we end up in here with the mu of 1 over 1, which is 1, and the mu of P sub I is equal to negative 1, because it's negative 1 raised to the number of primes contained in n. There's only one prime, so this is P sub I. And now, since phi is multiplicative, I actually still have it in here. So from here, So we have this. All right, so this is this is equal to this. All right, and now we have this is going to equal to I equal 1 to R and 1 minus p sub I. Actually, 1 over p sub I. And there is, of course, the, let me actually write it from, but there is another thing in here. All right, then finally we have P of n by the formula, this is equal n, and now with the summation of I, actually D. Let me see how I'm going to write this one actually. Right, I have got one thing in here, so in here, actually I should need to go back to this one, that's why. So from here we have the phi of p sub I, k sub I is equal to p sub I, k sub I times this. And now we need to put this back in here with phi n is the product of all of these I equal 1 up to R di k sub I 1 minus 1. Now when you take the product of the p sub I, the p's here, you get n. Let me do a good job here, don't want to rush it. Okay, so this is equal the product of pi ki, I1 to R, and then the product I1 R1 minus. The fifth one, this product is just n, okay? The product of all these p's is n. And we get the formula. All right, there's another proof, as I said, using the fact that mu is multiplicative. All right, not phi, which is a bit stronger because in here we kind of using the same idea that phi is multiplicative the way we derived actually this formula earlier. Here is another derivation that does not depend on this. There's a proof of the corollary that does not use the phi is multiplicative. Uses a mu is multiplicative. All right, so let's look at again phi of n. This is equal n, and d divides n mu of d over d. Now remember that a divisor, d divides n, if and only if d is equal pi a sub I, b1, we put b1, a1, b2, a2, r, where these a's could be equal to 0, meaning they are missing, or could be less than or equal k sub r, or every r. So a divisor consists of sum of the primes, okay, involved actually contained in n. Some of them could be missing, and some of them could be smaller than the case of r. So in other words, the phi of n, then we can write as, I'm going to leave the n by itself, and then I want to write this summation as to be over the P1, A1, P2, A2, and so on. That's the D's. PR, AR. And also having the A sub i's here, less than or equal, K sub I bigger than or equal to 0. And then we have the mu of these different divisors. 1, A1, P2, A2 up to PR, AR over this product. I equal 1 to R, EI, AI. All right? Now, we know that the mu is multiplicative. So we can write this as summation. I don't want to repeat what's written underneath, it's the same. There's an n, first of all. So this is n, and the summation. And this one, I can take mu of P1 to the A1 and so on. So I could write this as a product. I equal 1 to R, the mu of PI A to the R over the product of same product, DI A sub R. All right, now let's write what is in this sum again. We're going to see that there's only a couple of pairs that are not 0. Now, since the mu of PI AI is equal to 0 for every AI bigger than or equal to 2, then we have this. Phi of n is going to be equal to n, and the product is I equal 1 to R of the mu of 1 over 1 plus the mu of PI over PI. And that's it. Any other ones coming from here, they're going to contribute 0, nothing. And then we, of course, have the last thing in here. This is equal to n. And this product in here, we have 1 minus, and this one is 1 over P sub R. And then we have the product, of course, in here over all these ones. I equal 1. Again, we haven't used here phi is multiplicative, only we use the mu is multiplicative, Mobius function. All right, well, this ends actually chapter 7, all right? And I think this is the material that will be, for exam number 2. So chapter 5, 6, and 7, all right? I'll stop right